So the topic for this hour, and I guess also the next 1 or 2 hours, is probability theory, because we need these epsilons, as previously explained. Probability theory. There are two things that we want to talk about. The first thing is more of foundational issue. So first, foundations, to basically remind you of what you might have heard about probability previously or maybe not. And then the second one, Gaussian distributions, and specifically multivariate Gaussian distributions. So that's then the second big topic. And actually, this introduction to probability theory, foundations, Gaussian distributions, that's not only of interest for the general linear model, but that's of interest for a lot of stuff that is going on in cognitive neuroscience, because a lot of the stuff that is done in cognitive neuroscience uses probabilistic models. You can, from my perspective, you can formulate the whole thinking about the human brain in terms of probabilistic models, and everything that is not formulated as a probabilistic model is just a special case of a probabilistic model where the variance of the probabilistic aspect goes to 0. In general, probability theory is a very sensible thing to have, because it allows to reason about things involving uncertainty, and everything is uncertain, and probability theory is just a mathematical description of that. So what I want to say is that the stuff that we're going to discuss in the next 3 hours, I guess, is not only relevant for the statistical methods course. It's actually relevant for everything, and it's actually the most reasonable thing to talk about in general in science. I leave it at that. I mean, I could go on, but that would lead us far away from what I actually want to do. So then in the foundation aspects, so our first session on foundations, we want to talk about random variables. So I will tell you what I mean by a random variable, and then importantly, joint distributions. So that's really the meat of the next hour. This will lead us directly to conditional probabilities. Which, when we are there, then why not talk about Bayes' theorem, because that's just a statement about conditional probabilities. Actually, the only reason why I'm introducing conditional probabilities in this course is not because we will do that much of Bayesian inference, but we need to talk about independent random variables. And it's really independent. It's virtually impossible to understand independent random variables if one doesn't know conditional probability. And then finally, in terms of these foundations, we need to talk about discrete and continuous random variables, and the associated concepts of probability mass functions and probability density functions. So that's basically the plan. The plan for the first part, so for the foundations, and then once we have done that, we can talk about Gaussian distributions. The whole intro to probability theory is kind of a semi-mathematical intro, so of course there will be kind of formal expressions. It's mainly inspired by the writing that you find in applied probability theory, things like machine learning, maybe applied statistics, these things. So we are not going to talk about the real mathematical theory of probability theory, which is actually based on the Kolmogorov axioms, is a sub-branch of measure theory. Has any one of you encountered the concept of a sigma algebra? No one. Okay, so then no one has actually encountered the mathematical theory of probability. The thing is, the way that and we will talk about probability theory, that actually goes a long way, and you can do most of your daily probability or probabilistic modeling without going back to the foundations, so the mathematical foundations. In the end, you need them, and in the end, to really get a good understanding of probability theory, you need the mathematical foundations. But we don't discuss them here. I think I will make a supplement video that briefly explains what I mean by the mathematical foundations. Good. Having said that, we can actually start with talking about random variables with a definition that is not really a definition or anything really useful. It's really useful, but it's useful for us, but it's not useful mathematically. So what do I mean? Random variable. I have this great definition here. X is a random variable if X takes on random values. Kind of the worst definition of a random variable from a mathematical perspective, but from the perspective that we need, it's actually really helpful. So what you should associate with the idea of a random variable is that, in contrast to the things that we have seen previously, where you had these symbols, for example, y, and then y would be a specific number, for example, 3.2. If I say something is a random variable, you should think intuitively as follows. So this, if x is a random variable, so x is now a random variable, then x can take on values randomly. So x can, for example, be, somehow I will shift this, it's really annoying. X can, for example, be 0.1, or it can be 0.7, or it can be minus 0.1, or it can be 1. So it can take on random values. And the idea of probability theory and talking about random variables in our context is, of course, that we make some statement that defines in some way how it takes on these random values. Yeah, so it's not like that anything goes, but we will actually associate probabilities with the values that a random variable can take on. And if we start with the idea of what we will later call discrete random variables, and which will be associated with the concept of probability mass function, then we can say something like that, and write something like that. This statement Px equals x I is supposed to be the probability that x takes on the value xi. Yeah. So let's maybe put that, or let's revise this and write it up nicer again. So Px equals xi. This you should read as the probability that the random variable x takes on the value xi. Yeah, so this is what this p brackets x equals xi should mean. Yeah. About probabilities. So what do you know about probabilities? Anything that you know about probabilities? Is this a meaningful statement? So P x equals xi equals -2. Do you think that's meaningful, or no? Why not? Come on. Why you don't think it's meaningful?
Because many probabilities are sensitive.
Yeah. So I think you have an intuitive feeling, and also from your background studying, that the maximal probability that something can happen is 1, or maybe more familiar to you is 100%. So who's more familiar with 100% probability than 1? You didn't care, never ever thought about it. Okay. So probabilities are defined either between 0% and 100%, or 0 and 1. And we will really use the definition of probabilities being defined between 0 and 1, because that's the mathematical way. So there are these percentage probabilities. That's conflating a lot of concepts in terms of large sample frequencies and so on. So we use probability theory from the mathematical perspective. And in this sense, probabilities can only be between 0 and 1. And then, for example, if you consider a random variable x, which might take on values in 1, 2, 3, 4, 5, and 6 in this set. And we say, okay, let's say x takes on the value 1, 2, 3, 4, 5, or 6 with equal probability. Then we can say something like the probability of x being I is 1/6. Yeah, where I is, we can write it like this. I is in there. So what is important here is that you first of all get used to the notation that there is something like a random variable that can take on values, and to this to the fact that this random variable takes on a given value, you allocate a probability, which is a value here in the interval from 0 to 1. Yeah. So to give a concrete example for the thing that I just wrote up here, so if you think that the random variable here x models the outcome of the throw of a die, of a fair die, then you can say, or then this notation here means the probability that the die comes up with 3, for example, 3 dots, is 1/6. Can also make we can give another example where we actually describe a coin. That's the other very familiar example. So we say we have a coin C. So we model our coin by a random variable C. C can take on two kinds of values, which are
Head and number?
heads and tails, or number and heads or whatever. So H and T, I think, is the normal one. And then if you have a fair coin, what's the probability that...
1/2.
Yeah, so then you can say the probability that C equals heads is 1/2, and the probability that C equals T is also 1/2. So what is really important about this thing that we just brought up here is that you start to dissociate reality and mathematical model, yeah? If you haven't done so. What I just wrote here are mathematical models that may or may not describe things in real life, yeah? So there may be some die that if you throw it many times and you compute some averages, that roughly follows something like this. But this just means that this is actually a good model of a die. And the same thing for the coin. So if you throw a coin many times and look at how many times head comes up and how many times tail comes up, it may turn out that it actually is roughly in 50% of the cases. But that is real life, and this is a model. Yeah, and again, if it comes out roughly 50% of the cases, then that's some indication that this is a good model. This is not this is not a pipe. This is not a coin. Yeah, this is a mathematical model. And the good thing about this mathematical model is that you can compute with it. So you have probabilities, and probabilities of different events add up to 1. So the basic probability that something happens is 1, and one can do the whole probability calculus with that. That's all great. Whether it is in line with reality, that may sometimes be the case to a higher degree and sometimes to a lesser degree, but it's not a statement about real life. This is confusing because these early examples that one always is used to in probability theory always use like these games of chance, essentially, so dice or coins. But dissociate that. There is no real probability. Probability doesn't exist. It's a mathematical model, and based on this background, we basically now go on to talk about joint distributions of random variables. But before we do so, are there questions about what I just said? No? Okay, so see the whole probability issue as a probability stuff that we talk about, see this as a model. That means as a language where we have symbols what are called x, and we say this is a random variable if x takes on random values, and then we can write statements like the probability that x equals some value is some number between 0 and 1, and but that doesn't mean that that x is the same as the die that you see in front of you. It's a model of the die. Yeah, probability theory is a model. It's not real. It's a model. Good. What you need to basically become familiar with is this notation that you have something that we might call x, for example, that can take on specific values, for example 2, and you allocate to it a probability in, for example, 0.1, so in the interval 0,1. And what actually is, and I think you're familiar with that, and you have seen these examples like coins where it's 1/2, for fair coins, or dice where it's uniform. What is really important to get into the GLM and the notion of multivariate Gaussian distributions is the notion of joint distributions of random variables. And that's actually not that hard. So we will now talk about joint probability distributions. Again, what we will later call discrete random variables. Yeah. So we assume we have two random variables, x and y, and x can take on values like this, 1, 2, 3, and y can take on values 1 and 2. Yeah. So I'm using an example now that is not in the script to make things a little bit easier for me to write up. This notation, what I'm writing here is, don't think too much about it. It's essentially just, the only thing that I want to say here is that x can take on the values 1, 2, and 3, and y can take on the values 1 and 2, and they cannot take on any other values. Yeah? That's only what I want to say with this statement. Now, like I just told you that we can say something like p x equals 1 and then associate a probability with that. We can also associate a probability with the scenario that x takes on a value, so x equals xi, and at the same time y takes on a value, yeah, so y I. And there are now 3 times 2 cases of what can happen that x takes on a value and y takes on a value, and it's useful to put them into a table. So there are these cases, so x can be 1 and y can be 1, then x can be 1 and y can be 2, x can be 2 and y can be 1, x can be 2 and y can be 2, and x can be 3 and y can be 1, and x can be 3 and y can be 2. Any mistakes? So x 1, 2, 3, y 1, 1, 1, x 1, 2, 3, y 2, 2, 2. Yeah. So these are the possible cases if x can take on the values 1, 2, 3, and y can take on the values 1, 2, and we are interested in the case that x takes on a value and y takes on a value. Yeah. What I did here is just I tried to have the first number be kind of the row and the second number be the column. It's not really important. We're not going to do matrix multiplication or anything with that, just to have it in a organized way. Yeah. Questions about this? No. Good. Now the idea in terms of joint distributions is that we have what we will call a probability mass of 1 that we can distribute over these cases. Yeah, so we say we have our entire probability that we can allocate in our little probabilistic model here is 1, and now we can split up this probability mass of 1 in such a way that we cover all our cases here. So let's get rid of that because that was just pure intuition. But let's write something up. Now, for example, the following. The probability that x equals 1 and y equals 1 is, let's see how many cells we have, 1 over 6. So that is 0/6. The probability that x equals 1 and y equals 2 is 1/6. over 6. The probability that x equals 2, y equals 1 is also 1 over 6. Probability x equals 2 and y equals 2 is 3 over 6. Probability x equals 3, y equals 1. How many do we have? We have 5. So then let's give this daring. So let's give this 1 over 12 and this y equals 2 also needs to be 1 over 12, because in total we have a probability mass of 1 that we can distribute over these cases, and now we have 0 plus, so let's maybe write that down. So we have 0 over 6 plus 1 over 6 plus 1 over 6 plus 3 over 6 plus 1 over 12 plus 1 over 12. So that's 2 over 12 here, so that's 1 over 6. So these are 1 over 6. And then we have 1 plus 1 plus 1, that's 3, plus 3, so we have 6 over 6. So we have distributed our probability mass over these cases. Yeah, everybody happy?
How did you get the 12s? I don't understand how it changed.
I just needed, I wanted, okay, so anything here that I just did, the only rule that that was there was that I have a probability mass of 1 that I want to distribute over these 6 cells. Yeah. Besides that, I made everything up. Yeah. So there was nothing that tells you from these numbers. So there was nothing that here with the 3 and the 1 that led me to 1 over 12. I just made everything up. And I can also, just to annoy you, I can also say, oh, whatever, let's say this is 0. And this is 1 over 12 now. I still distributed the probability mass of 1 over these 6 cases. And what I just did was to write down a probabilistic model. So I just made a probabilistic model. And now it's there in digital form. So the only rule that was happening here was that there's a probability mass of 1, everything else I made up. But now, based on this probabilistic model, in this case, what we will call later the joint distribution of 2 discrete random variables and the associated probability mass function. Based on this probabilistic model, I can actually ask you something and you will be able to answer that. So for example, if now I have this probability distribution here, which I now call Px, y. Yeah, so this table here, I now call a probability distribution. I write for that Pxy. Now think that I can sample from this probability distribution, yeah, so that I can draw samples somehow from this probability distribution, for example, with a random number generator. And I now ask you, I now want to take samples from this probability distribution with some random number generator, and I'm looking at these samples, and one sample that I'm particularly interested in is the sample that I sample x equals 3 and y equals 2. How many of these samples will I take from this distribution? So how many samples will have the form x equals 3 and y equals 2 when I sample from it? 0? Why 0? Because the probability for that to happen is 0. Yeah. So you said 1. Why did you say 1?
So there's one example of it.
Yeah, okay, it makes sense that it's 0. And basically based on this distribution, it will, if I sample from this distribution, I will never observe this. But now if I ask you, I'm taking samples from this distribution, and I'm now interested in the case that x1 is 1 and y is 1, and I'm also interested in this case, x2, y2. So which of these cases will I observe more often when I take samples? Why?
Because it's 3/6 versus 1/4.
Exactly. So you have, from this, I just want to demonstrate that you have a very good intuition about the whole thing, even if you haven't seen this notation previously. Yeah. So that's in a way the thinking that you always need to associate it with these kind of statements, and that's exactly what the whole thing is about. The difference maybe is a little bit that in the probability theory calculus, the only thing that you actually do is to calculate with these probabilities, and you never actually sample something. So you sample something when you write, for example, a computer program with a random number generator, and then you can sample something. Or when you look at such a table and you ask yourself, what does that mean? In mathematics, you don't sample. So there's no notion, there's no symbol now that means take a sample from this. It's a subtle point, but in a way it's important. Okay, so what I've demonstrated are two things so far. So first of all, I said there are two random variables. They can take on values, and I can, whatever I want, associate probabilities with them. There are two rules, though, that the sum over all these cases equals 1, and that the probability needs to the probability that I allocate here needs to be between 0 and 1. Actually, that the whole thing adds up to 1. We can also express using the sum symbol. So just to use the sum symbol, we can say, okay, if we sum over all x values, so going from 1 to 3, and we sum over all y values, so going from 1 to 2, then p x equals I, like this here, and y equals j is 1. Yeah, this is not surprising because that's how I first defined the whole thing, and I just wrote up in a sum symbol form the fact that these 6 numbers here, 1/12, 1/6, 1/12, 1/6, 3/6, and 0, they add up to 1, as I already showed you previously. Yeah. So this is just, this is also sometimes called that probability distributions are normalized. So they, if you add all the probabilities of a probability distribution, more precisely, if you add all the values of a finite discrete probability mass function, you get 1. Now, we have written down here what I call a joint probability distribution over 2 random variables. But when we do so, what we also get are 2 other probability distributions over a single random variable each. Yeah, and this is what I want to show you next, namely the idea of marginal distributions. So let's call this, just for completeness, let's call that joint distribution. and now we talk about marginal distributions. So if you have a joint distribution over two random variables, there are two marginal distributions, which are, of course, the distributions of the individual random variables in your joint distribution. So, for example, if you have a joint distribution over 5 random variables, then you have 5 marginal distributions. And the marginal distribution is just the distribution of the individual random variables. So here we have a joint distribution with a random variable x and a random variable y. And now we are interested in only the distribution over x. So basically we ignore the fact that x can be 1 while y is 1, and x can be 1 while y is 2, and we are just interested in the case that x equals 1. Now, to obtain this probability, we can simply add the probabilities that happen when x is 1 and y takes on one of its values. So marginal makes sense to call that marginal because we can put it here at the margin. So here we can write p equals 1 is 1 over 12 plus 1 over 6, because think of if you sample from that, then you will have cases where x comes up 1, y comes up 1, and x comes up 1, and y comes up 2. And if you're now interested in only the cases, or only considering x, you can add the cases that came up as y equals 1 and y equals 2. So not over 16, of course, but over 6. So you get, this is 2 over 12, so 3 over 12. For p equals 2, we have two cases, y, like always, of course, y equals 1 and y equals 2. So we have 1 over 6 plus 3 over 6. That's 4 over 6. And we have for p equals 3, we have again two cases, 1 over 12 plus 0. And now if the magic is supposed to work, then actually this should also be a probability distribution, which means that it's normalized, which means that the numbers should add up to 1. So if we consider now the sum from I 1 p x I, then we have 3 cases, so I'm just writing out the sum. P x equals 1 plus p x equals 2 plus p x equals 3. There we have 3 over 12 plus 4 over 6 plus 1 over 12. So 4 over 12 plus 1 over 12 are 4 over 12. So we have 4 over 6 plus 4 over 12. Then we can divide this all by 2. So now we have 2, 6. And then we have 4 over 6 plus 2 over 6, 6 over 6. So we have 1. So we see that this is actually a probability distribution over x, just by summing over the values that y can take on. And this distribution here, Px, where of course x can take on only the values that x could take on in terms of its joint distribution, is called the marginal distribution. Yeah? The marginal distribution of x, and it's denoted by Px. So that's marginal of x. Now, as I said, there's also another marginal distribution. So we have already found our Px, where essentially what we did is that the probability for x taking on the value I is given by the sum of the probabilities that y takes on j. So this is just again in some form what we have done there. And then of course there's another marginal distribution, namely the probability that y takes on its values. And how do you think we compute that based on what we've seen for x? Any suggestions?
From I to 3, sigma, like you should add up from I1 to 3.
Yeah, x1, 2, 3. Yeah, where I, so I sometimes call the value that x takes on y. Exactly. And it's actually helpful to then, in terms of this thing, write that here, for example. So the probability that y equals 2 is given by the sum of these values here, like you said. So x being 1, 2, 3. So 1 over 6 plus 3 over 6 plus 0 is 4 over 6. And Py equals 1 is 1 over 12 plus 1 over 12. That's 1 over 6 plus 1 over 6. That's 2 over 6. And again, you already see there that this 2 over 6 plus 4 over 6 is again 6 over 6. So it's again normalized. So just in terms of what we just did, we now summed the probabilities over x, and in this way have computed what are called marginal distributions in a joint distribution. Yeah? Again, the whole thing that these marginal distributions actually are probability distributions in the sense that they normalize. Of course, this only works because in the very beginning I defined the probabilistic model, so this joint distribution, in the way that the probability mass of 1 is distributed over these 6 cells, so that all the probabilities that are in this table, they add up to 1. If this is the case, then if you sum the probabilities over columns, as we did for the marginal for x, or you sum over the rows as we did for the marginal of y, then these distributions that you get out of that or these things that you get out of it, they are again probability distributions. Yeah. Okay, I think I stop here for today. So we have seen, to summarize, what I try to introduce is fairly sloppy in mathematical terms to say x is a random variable if it takes on random values. Then I've made the point that probabilities, as you know, are values between 0 and 1. I emphasize, and I will again emphasize, that this is all a mathematical model. It has nothing to do with the real world. There is no real world probability. If you say the probability that it will be crowded at lunch if you go there now is 0.8 or something, that means that subjectively you think, based on your previous experience, that it might actually be crowded. but it doesn't exist outside of the world, and maybe it's actually a wrong model today, because today is a bridge day. So maybe today is actually not that crowded because because a lot of people take off. So maybe your model then was wrong. So there is no real probability outside of your head. And then we discussed a joint distribution, and we've seen marginal distributions in joint distributions. Questions? No questions? Okay, then please again practice matrix multiplication, and please also compute the probabilities that you've seen in this table. The best thing would be actually that you do the study questions the study questions are not only there as the final exam questions, but they're actually the study questions that you can use to revise and prepare each week's session. So a good way to come prepared to the next session would be to do study question 3 and look at it. So don't compute the conditional probability distribution because you don't know what that is yet, but compute the marginal distributions. Yeah? Good. And we will then continue next week using marginal distributions to compute conditional distributions. Good. Then see you on Thursday or Saturday.